All right. Hello, everyone. Hello, everyone. So, um, before get started on the next section, just want to go through the second part of the photometry notebook quickly. And again, the empty cells are mostly for you to practice your Python and plotting things. Like the actual photometry are already done. So you should still go back to your notebook and try to finish it. And a lot of it is just copying and pasting from the aperture photometry section. So that gives you a nice excuse to kind of like revisit how all these different cells work. But essentially for our PSF photometry, the first step is to construct a PSF model. And this is when I said, you take the data, all the stars, and look at the shape of it and come up with like an average shape. And this is done here. We're using a software called PSFX, PSFEX here. And just take some config file. And this is something you have to go in and kind of edit all the parameters. Like learning how to do this is art and science of like in itself, but here you can just run it, and yeah, it will take your image and like a source extractor catalog and go through all the stars and construct your PSF model. It takes a while, as this warns you. It's not multi-threading. But then after that, it spits out this file, which is just the PSF model, and you can plot it. And that's what it looks like. Yeah, and then here it's just a 2D radial profile. Sorry, the 1D radial profile of this image. And you can see it is it's kind of like a Gaussian or Moffat function shape. And right, so after you have this PSF model, you can rerun source extractor, but this time you give it this parameter PSF name, and you give it the PSF fit file from here, and it will redo all of the source extraction, but this time including PSF photometry. I don't have to run this again. I just did it. This takes a little bit longer than just source extractor, also a lot of lines. Yeah, and then you get the same kind of output table out that you can read back in, do the same cross matching with the catalog that you have earlier. And then this is the PSF photometry as a function of like catalog magnitude. And you can see, if you remember, the plot we have from earlier from aperture photometry has a bunch of different lines depending on the size of the aperture you use. In this case, it's just the PSF, so just get one value. Yeah, and then you're doing all the same things, 0-point derivation, and finally you get the PSF photometry magnitude of this target V6416, which is like some kind of recurrent nova, and PSF photometry is 14.98. And if you go back to aperture photometry somewhere here, you can see that that's kind of consistent with aperture photometry if you use a pretty large aperture. So yeah, just a quick go through. If you have time this evening, should go through all the empty cells again and try to recreate this. And all the solution will be posted after the workshop. All right, now that we got a 5-minute run through of PSF photometry, let's move on to the second part of today, where we'll be looking at transient light curve analysis. And Looking here, I only have 15 slides, so hopefully y'all have a little bit more time to work on the notebook. Without further ado, let me start. All right, so for light curve analysis, we started this week by looking at astronomical images. And this morning we run astrometry and photometry to try to measure how bright sources of interest is in our images. And now what do we do with that information? And the answer is many different things. For instance, people who care about transiting exoplanet can take photometry, plot them up, do really careful photometry to try to see the dip in the light curve. And the light curve is just a magnitude as a function of time of your source. Right, Kritapad mentioned like AGN or quasar reverberation mapping, which means you track the variability in these supermassive black holes in distant galaxies, and you can see variation that have time delay between different bands because the emission comes from different region in the disk, things like that. There's truly so many things that you can do with light curve. We will look at one thing we can do today, which is to look at evolution of transient objects. And by transient, I mean things that kind of, don't, it's not there before, it shows up for a brief period of time and then goes away, of order a year maybe, or even shorter. But really, the title of this should be Blackbody Radiation, Spectral Energy Distribution, and Bolometric Light Curve. But that title is just scary. So the goal for this section are a bit briefer than the one in the morning. So first, we will touch upon a little bit upon something called blackbody radiation. Have anyone not heard about blackbody radiation before? Oh, okay, that should be easy then. And then we will look into how to fit a curve or a model through data, something kind of very similar to PSF fitting that we just went through super quickly. But now we get to try to do it ourselves, but just in just for one-dimensional data. So it will be easier to do. And lastly, we will learn how to make a bolometric luminosity using observations in multiple bands. So how do we estimate total light curve or total energy coming out of a transient? On the left here, I'm showing a figure from my recent paper, and this is a kind of like a spectral evolution of a supernova. On the x-axis, that is the wavelength, and on the y-axis is just like normal light flux. And you can see that there's so many things going on there. Each line is just a different observations that we have, and we'll talk spectroscopy tomorrow. But this is just to show that the distribution of light across the even just the visible band has a lot of detail in it. So usually when we observe objects, be it supernova or other things, we don't get this kind of coverage as so many epochs. Usually we just get photometry, maybe because we don't have access to a spectrograph, or maybe because the optics are way too faint to perform spectroscopy. This supernova, for example, was relatively bright, so it was really easy to obtain a lot of data. And usually we don't have this. So in most cases, we have on the right the filter pass bands I showed in the morning. Yeah, earlier today in the morning. And this is just the flown UTRI filters. Usually we just get photometry in all these bands. So how do we go from this to try to estimate something like that from above. Yeah, whatever direction that yes. And this is something we call a spectral energy distribution. It is essentially a spectrum, but instead of having data at all these different wavelengths, we just get data from our photometry. So here in this plot, I'm showing just a spectral energy distribution, or SED, of this one supernova called 2014C. And you can see there are some spectra that are plotted in like this faint line in the background. So in some bands, we have spectra, but in others, we just have a data point, and that is photometry from an image. In this case, most of these are in the infrared, but it applies in the optical as well. So while like real spectra have a lot of information in it, you've seen all the lines and ripples and all of these things that we'll see tomorrow morning. Usually for really broad features, which is essentially just the temperature of the object, you can tell simply by looking at like a few different photometric bands. You don't need a full spectrum to do this. And this is kind of like the core point of our exercise in this section. So let's do a very, very, very quick introduction to blackbody radiation. This is kind of like a physical question that confused 19th century physicists, and it's one of the kind of like the origin of quantum mechanics was a bunch of people trying to figure this out and stumble upon the really weird fact of our physical world. But the question is this: if you have some kind of idealized object that can absorb all of the light going in and only return energy out in as like thermal radiation, what would the spectrum look like? Max Planck figured this out in I don't remember the year, 19 something. Can look up on Wikipedia. And to come up with these two equations that we now know as the Planck's function, he has to make a really bizarre assumption, that is, light can't just come out in any arbitrary amount of energy, but light has to be emitted in like these little packets, each of which has energy proportional to the frequency. And when you put that assumption in, you can derive these equations, and you can explain blackbody radiation. The details of this is way too much, way beyond our 1 hour section. So, wait until you have your undergraduate E&M class and you'll get to learn it all, or maybe you already know about it. But we will simply use this equation to fit our data today. Kind of two different, not really corollary, but results of this blackbody radiation is that, one, you have a peak wavelength of an object is just dependent on the temperature, and this is called the Wien displacement law. If things get hotter, then the peak wavelength displaces into the blue, and the equation is just simply that. Here I have a pretty nice picture of a double star. Anyone know? Oh, I guess it's already spoiled. It's Albireo in the Cygnus constellation on the opposite side as Deneb, but it's kind of like I forget the latest on this debate, whether or not it's a visual binary or it's a real binary, but the two components have very different temperatures, so you can see these two different colors. And turns out stars are like very well approximated by blackbody, and these are kind of like the best examples of real black bodies that we have in the universe. Another thing is that we can integrate the Planck function from frequency of 0 to infinity and get a total black body luminosity. And this just depends on the T, the temperature of the black body, and also the radius. So the emission flux at the surface of the object is just proportional to T to the fourth with this constant of proportionality called the Stefan-Boltzmann constant. The fun part is that you can actually derive it by doing a really wacky integration of the Planck function. And this is the like all the fundamental numbers and constants that the Stefan-Boltzmann constant depends on. And finally, you can get luminosity simply by multiplying this flux, which is sigma T to the fourth to just 4 pi r squared, the surface area of your glowing orb. So, as I mentioned, stars are quite well approximated by black body. So if supernova near peak, on these plots to the left here, I'm showing ideal thermal spectrum. That is the black body curve, and then plot next to it is the actual stellar spectrum from that temperature. And you can see that sure you have like all these absorption lines from different elements, but the overall shape is still pretty similar to black body. And this is the reason why we can just use a few photometric observations to gauge this shape of the so-called continuum of the spectrum without needing a full spectroscopy. The three plots on the right show the evolution of another supernova from earlier time to later times. And similarly, you can see that the full spectrum has all these like bumps and wiggles from different atoms, but the overall shape is still pretty well matched by the black body. And here on the top is a 5500 Kelvin black body, and at later times, the temperature shape. And you can also see that in these bottom two plots, the general shape kind of depart from the black body quite significantly, and that's because weird things happen. Another thing that I want to mention before we get to the exercise is how to convert magnitude to flux. So we already talked about this in the morning. We just essentially flip the equation, right? So you can satisfy yourself by just writing it down, but it's essentially the flux from a magnitude is just the 0-point flux multiplied by 10 to the minus magnitude divided by 2.5, and that gives you the flux. And again, F naught, if it's Vega, then you have to look it up what F naught is. If it's AB magnitude, then it's always 3631 Jansky. So here, if little m, if this magnitude here is an apparent magnitude, then the F that you get, the flux, is the flux that you observe here on Earth. If m is the absolute magnitude, which is something that we will encounter in the working notebook that we will look at later today, then this flux is the flux you observe at 10 parsec away from the source. Just keep this in mind. You'll get to use this. And then again, if you know flux at 10 parsecs away, then you can just compute luminosity. So with all those, and we can scroll back through it if we need to remind ourselves. Let's talk about how do we fit a line through data. There are several different ways to do this, but the most classic is something called a least square optimization. So in this problem, we have a bunch of observations. Just call them O with an index I, so just a bunch of observations. And we think we know how to explain this observation with a function, just a model, the function called f, that takes in some X value. So that if like in this context, you can think of O as a flux in different bands with a like this underscore I is like a say a wavelength of different bands, and then we have a model to explain this SED. So this function takes in the wavelength, then takes a bunch of other parameters here. This is say arbitrary ABC, whatever, it doesn't matter. The problem we are trying to, or the process that we are working through here is how do we adjust parameters A, B, and C, D, E, F, whatever, in order to modify our model to get as close as the observation as possible. And this is called least square optimization. You can do this by adjusting A, B, and C to minimize this sum, which is just the difference between observation and the model squared. And there are several algorithms to do this. In the interest of time, we're not going to go through them, but we will instead use a package from SciPy. There's a routine called CurveFit that can do this for you. And if you go into the documentation of CurveFit, it will tell you all of the nitty-gritty details of how it does the least square optimization. But the kind of a really brief intro is that you don't need to randomly adjust A, B, and C, and then see what is best. There's a kind of a methodical way to update these parameters to get better and better and better answer every time. These days, least square is kind of looked down upon a little bit. And the reason is because there are several issues with it. It has several underlying assumptions that are not always true and are especially not true for astronomical data a lot of times. So for example, least square fitting assumes that all your uncertainty that you input with the data are normally distributed, have a follow Gaussian distribution, which is definitely not true for a lot of astronomical data. It also assumes that there's no uncertainty in the X direction, all the uncertainty is in Y, and that's also not true in a lot of cases. So a more modern way to do it is called Markov chain Monte Carlo fitting, and kind of a very popular package to do this. The paper has like 10,000 citations. It's called MC, and I put a link here. Please go through the tutorial. It's really instructive to read through the process. But the kind of a very brief one sentence summary is that instead of trying to be methodical about adjusting A, B, and C to get the best model, MC just do it all. And then that way you can like actually see the distribution of the probability distribution of all the parameters that you're trying to fit. The problem is that you could not have done this 30 years ago because your computers are not good enough. So lastly, how do you construct volumetric light curve? We talked about this briefly in the morning. That volumetric light curve is or volumetric luminosity or magnitude is the magnitude, assuming that you know the emission from like at all wavelengths from a source. You don't observe this. You observe just a few bands, and then now you're trying to come up with the best estimate of what the volumetric magnitude is. To do this, you both have to interpolate between different filters. So say if you have only observation in U band, R band, and C band, but not D and I, then you have to interpolate and fill in these missing filters. And also you have to extrapolate because there are also light in the near infrared that maybe you don't observe at all, and you don't have anything at longer wavelength to provide you with like a place to estimate. There are several packages to do this. Again, these are, very common problem in astronomy. A lot of people have to work through it. So we wrote a bunch of packages to help us do it correctly. And the most used ones, at least in astronomy, in supernova science, are called Super Bowl and Extra Bowl. So Super Bowl is the original one, and Extra Bowl is kind of like the updated version with more features. So this software can interpolate the and fill in the gap between different filters that you don't have observation. And they can also do the extrapolation and try to estimate the unobserved, like infrared and UV light. What it does is that it fits blackbody curve to your observation, then sum up all the observed flux, and then come up with the estimate for the unobserved flux. Now, we will write today, just for fun and instruction, we will write our own blackbody fitting script. And for us, we can be a little bit simplistic, and instead of dividing the supernova light into observed and unobserved flux, we will just forget about the observation altogether. We'll just fit like a blackbody through it, and then we will just get the magnitude just from the model. So we will just get the blackbody luminosity out of the process, and the notebook will guide you through that. So that's the game plan. I provided you with the light curve that I stole from this paper from Matt Nichols 2016, and this is just from the GitHub repository for Super Bowl. So this is their example light curve. So we can load it up. The data are provided in GR and I band. 3 band is good enough for us to run this exercise. The notebook will guide you through the steps. We will first plot the SED from different epochs of the supernova and try to see the evolution that happened. We will convert all these provided absolute magnitude to flux, and then we will plot the blackbody spectrum on top of it. And then on the last 2 steps, we will run curve fit to try to get blackbody radius and temperature out of the data. And then on the last step, we will write a for loop to do this at all the different epochs. At the end, we should get a bolometric light curve out. Before we get to that, any questions? Went through everything kind of quick. So if you have any questions about SEDs, about blackbody radiation, when we are looking at the notebook, you can always ask. So let me pull up my own notebook. So for this one, it is quite simple. You just need to copy the SED fitting. Oh, this is the solution. Yeah, so for this, you just need a notebook. So you just copy this notebook, SED fitting.ipython notebook, to your working path. And then the data, it's just one file, and it should be correctly pointed at. But if you have problem loading up the file, And this notebook is mine. So if there are problems with it, then it's all my fault. Yeah, so first it will read out uh, the light curve, which is in just a text file. Get this, and then you can select specific columns. This is how you can use AstroPy table. You already see this in the morning. You can, yeah. So here in this case, I'm just selecting epoch, which is just the time of observation, G band. And you can also do the uncertainty like this. Then when you do this, you get the epoch, the G band magnitude, the G uncertainty. You also notice that the photometry is given to you in absolute magnitude, which is quite rare. Usually you get apparent magnitude, but in this case, it's already the distance to the source is already taken into account. Yeah, and you can, these are some examples of how to select different rows. You can just use the indices like this, or you can have a condition like you want supernova curve, given that the epoch is less than 0. So you want things before peak, like. Yep, and then from then on, it's a lot of things for you to build. If you still don't get the file to load correctly, please let me know. if you see a file permission problem, if it says that you don't have permission, you have to copy the Python notebook to your home directory. Using this copy permission, or maybe this. And that's the only file you need. But if you're trying to run the Python notebook from the ASTRO101 directory, it will not work because you don't have permission to write in that directory. So this is a light curve that you should see. Who does not have this yet? Please raise your hand so I can go help. I have a mistake in my notebook, so only some people can run it. If you still have permission error, change the data directory to this. So just use the home there. So clarify that just refers to the number of days from the peak light of so my 20 something plus 100 after. And for the SED pods, it will be very helpful to plot something early, something close to peak, and something right when you see the evolution. And if you get like index out of bounds issue, that might be because the epoch that you type in does not exist. So this goes tell that you print out the table and look up epoch. Anyone here not at the filter? But yeah. So have anyone not gotten to this SED part at 3 epoch yet? Oh, sorry. And just to make sure we all get the same answers at the end, these are the wavelengths of the filter. It should be lambda mean for the SDSS filters on the SDO website. Not the best. And if you get to the next part, which is just writing this function, all I want here is just in the future, instead of like typing all this down, I just want this function to spit out the SED, which is this magnitude list, and the uncertainty, which should be this uncertainty list. That is all. And if you're done with writing this function, when you test it, try different epoch as well, not just one epoch, just to make sure that um, that you're reading the input. And who is not done writing this function yet? If you can help there. right? In the interest of time, if you are not at the converting flux yet, here's the um, here's what you need for the function. It is just what you were plotting before. SED at epoch is just array of the SED at that epoch. So just G, R, and I. Um, and then the error is just so just be careful that the and yeah, that you're using this epoch to do the slicing and not epoch 1, 2, or 3 from before. So can you raise your hand if you're not at unit conversion yet? right? If you already go through unit conversion, these are the answers. If you're not here yet, please raise your hand. I'll go help you here. All right, for the black body radiation, um, this should be your test V mu array. If you're not here, let me know. Got 20 minutes left. Just want to make sure that means you get to see the light, the black body over the beam. So if you see this terrible fit to the data, and, and yeah, yeah, Um, Anyone else need help with unit conversion? Want to make sure we all get to at least fit one epoch. Unit conversion. Okay, before we take a break, let's make sure we get this fit. I got 3 minutes. So have anyone successfully run this one per fit? Hands? Awesome. So here, what we're doing is that we just need to fit some model, this function if new to fit to some data. And here the data that we are trying to fit is just this plot, right? Which has wavelength on the x-axis and the flux on the y-axis. So here x is just the wavelength array. And y uncertainties are just the flux that evolve from flux error. That's not like it. Oh, because yeah, that's not like things with units. So you just have to convert it back to the value. Yeah. So if you fix the unit issues, this is the fit that you get. And this is just for one epoch. Right, you can, yeah, you also have to write a function to compute luminosity, but this is the same thing. Just write this function in Python form. But then after that, you can just write a loop with all the same things as before, and you just loop through every single row in the photometry table that is provided. And after doing that, you can get the evolution of blackbody radius, temperature, and luminosity. And you can make it plot. Which should look like this. And then this supernova has been published, so you can compare it with the result in the literature. Which is this plot. No. Yeah. But yeah, so another challenge from this lesson is that there is another file with photometry, but that's the real file. So you don't get, there's some epochs that don't have all the magnitude. There are some like really bad values. So the challenge is to redo this whole exercise, but to produce the black body fit, but use the real photometry table, which has all the terrible bad data, missing epoch. So some epochs will only have 2 or 3 bands. You might have cases where there are 2 epochs, like an hour apart. Do you combine them? Do you not? Up to you. So that's a challenge. And now it is 3, so let's have a break. So thank you everyone so much for your attention.